Hello everyone. So welcome to another session of Control Systems with MATLAB. So during this session, we are going to discuss about block diagram reduction. We had seen in the class that we can reduce the given complicated block diagram into a single block, right? So the same thing can be done with the help of MATLAB also. So that is what we are going to discuss today. So, before we go into details, I would like to introduce you few MATLAB commands that we use for block diagram reduction. First one is called series. Okay, suppose you have two blocks in series. Then, what do you mean by series? Series means the output of one block forms the entire input to the second block. Okay, this is called a series configuration, if you remember. Right? Output of G1 forms the entire input of the second block. Fine. This is what is called series or cascade. Series or cascade configuration. Okay, so this command series, SERIES, okay, will give you the overall cascaded system. Okay, so what we have to do? So you need to define your numerator 1 of G1, okay, denominator 1 of G1, then you define your numerator 2 of G2, denominator 2 of G2. Okay, then you can make use of the command series. So how to use that? What's the syntax and usage? If you want to know more about the details, you can type help space series. Okay, that will display the syntax and the usage. Okay, so this is how to use the command, right? So keep in mind, input round arguments, within the round arguments, we give the input values. Okay, and square brackets are used to fetch the output values. Okay, so within the square bracket num comma din will give you the numerator of the overall cascaded system transfer function, and denominator will give you the denominator coefficients of the overall cascaded system. Okay, so that is about the command series. Okay, so you can see here, if you type help space series, it will give you the syntax and the usage. Okay, then there's a command called parallel. What do you mean by parallel? Two blocks are in parallel. When do you say two blocks are in parallel? It starts from the same pick-off point and ends at the same summing point like this. Okay, here we say that two blocks are in parallel. Okay, say that in this way plus plus. So it starts from the same pick-off point, the summing point or pick-off point, and ends at the same summing point. So we say that two blocks are in parallel. So in MATLAB, there's a command called parallel. Okay, so again the output remains the same. Square within square bracket num comma n equals parallel of num1 den 1 num2 den 2. Okay, then we have feedback configuration. What's the difference between parallel and feedback? Feedback means it starts from the same summing point and ends at the same summing point in a closed loop configuration like this. Okay, this is what we mean by the feedback configuration. So what's the difference between configuration 1 and configuration 2? This is the parallel thing. Okay, and this is the feedback. Okay, so in parallel, the connection starts from the same pick-off point and ends at the same summing point. Whereas in feedback configuration, it starts from a summing point and ends at the same summing point. Okay, in a closed loop, in a ring-shaped configuration. Okay, that's the difference between parallel and feedback. So the syntax is feedback num1 comma din1 comma num2 comma din2. Right? By default, MATLAB will assume a negative feedback. Okay, that is why it is given like this: feedback of num1 comma din1 comma num2 comma din2. Okay, but in case if you have a positive feedback, then we need to add an extra 1 here like this. Okay, by default, MATLAB will assume negative feedback. But in case if you have a positive feedback, then we have to give a +1 to indicate that it is a positive feedback. Okay, so if you have any doubt, what is to be done? Help space that thing. Okay, so help space feedback. Everything will be displayed. Okay, pertaining to the command feedback. Okay, it computes the closed loop configuration. You can go through that later. Okay, let us take one example and then try with all these things. Suppose we have two transfer functions. Say your G1 is this thing, G2 is this. Okay, I want you to try for all these 4 configurations. Okay, so what we have to do first? First, you need to define what is your num1. How will you do that? So how will you start with clear space all? Okay, CLC. Then you define your num1. What's your num1? 10. What's your din1? Open a square bracket. 1 space 2 space 10. Okay, then what is our num2? 5. What is our din2? 1 space 5. Okay, now what next? Num comma din equals. So first one is series. Okay, what will you write? Series. Round bracket. Num1 comma din1 comma num2 comma din2. Round bracket closed. So this will just give the numerator and denominator coefficients only. Okay, now how will you find the transfer function? Sys equals TF of num comma din. Okay, this will give you the overall transfer function, right? Let us try this example. That's what I have written here. Okay, so when you run these things, this is your overall numerator denominator. So sys equals sys s. Okay, I will give some variable sys s equals TF of num s ns comma ds. I have defined the variables as ns ds n1 d1 like that. Okay, so this will be the open loop transfer function. 50 divided by s cube plus 7s square plus 20s plus 50. Okay, this will be the transfer function, right? Now let us try for the parallel configuration. Parallel configuration, what happens? How will you do that for parallel configuration? So our numerator was this thing. Okay, so what should we write? We can give say something like this. Say num s or num p comma din p. You are free to give any variable name for the outputs. Okay, you are free to use any variable name for the outputs except for the keywords or the command names. Okay, so num p comma din p equal to what? Parallel what? Num1 comma din1 comma num2 comma din2. Okay, then what we have to do? We have to write sys. You need to find that in the system in transfer function form. Okay, so sys p equals tf of num p comma din p. Okay. Okay, so sys p equals tf of num p comma np comma dp. np comma dp. Fine. So this will be the transfer function when system is in parallel configuration. Okay, when system is in parallel configuration. Are you getting me? Okay. Now let us try when these two systems are in feedback. Okay. So what we have to do? Sys. So I will first put in negative feedback. Okay. Sys nf equal to what? Feedback of what? Num1 comma din1 comma num2 comma din2. Okay. So here I have used the variable names n1 d1. Okay. So that is what's shown here. Okay. You just need to give this thing. So this command will only give the effective numerator coefficients and denominator coefficients in the output variables nf and df respectively. Okay, so let us try this. So now what next? Sys nf equals tf of nf comma df. So that will give you the transfer, the overall transfer function. Okay, keep in mind we considered negative feedback. Now what we have to do if it is positive feedback? So as I said before, you will need to mention a 1 here. Okay, comma 1, right? So MATLAB by default MATLAB now it will understand that it is in positive feedback. Okay, so you can see that your numerator is different now. Okay, NF was 10 comma 50. That means 10 is 50. Sorry, denominator will be different. 1, 7, 20, 100. 1, 7, now it is 20 because it was positive feedback. Okay, So sys tf equals tf of nf comma tf, right? So this will be the positive feedback. This will be our transfer function when it is in positive feedback. Okay. Okay. So now let us take up one block theorem reduction problem. Suppose we are given with a configuration like this. Okay. So this is a block diagram given to you. Okay. So this is R. This is 1 by s plus 10. Here we have a block 1 by s plus 1, s square plus 1 whole divided by s square plus 4s plus 4. This block transformation is s plus 1 by s plus 6. And here it is a positive feedback, s plus 1 by s plus 2. Here there's a signal channel at negative feedback. Here there is a feedback at a gain of 2 with negative polarity. Okay, so we need to solve with the help of these commands. So there are two strategies to solve a given block diagram. So using series parallel feedback commands is one strategy. Okay, there is yet another strategy. I will tell you that later. Now, how can we solve this? How will you solve this? First, you need to see whether there are any blocks in feedback. Do we have any blocks in feedback? These two are not in feedback. Why? Because there's a summing pick-off point in between these two blocks. So they are not in feedback. So first you need to check whether there are any blocks in cascade. Do we have any blocks in cascade? These two are not in cascade. Why? Because there is a pick-off point or a take-off point between these two blocks. So these blocks are not in cascade. Are they in feedback? No, they are not in proper feedback. Okay. Then are there any blocks in parallel? No. So that means we need to shift summing point or pick-off point either to the left side or to the right side of the block. Okay, so let us assume that we are going to shift this pick-off point. Okay, so to which side will I shift this? When you try to shift a summing point or pick-off point, you must try to see 2 steps in advance. Okay, assume that I am shifting this summing point to the left side of s square plus 1 by s square plus 4s plus 4. What happened? When I shift this point to this side, these two will be in cascade. What next? You cannot solve it further. Okay. Now assume that you are shifting this pick-off point to the right side of s plus 1 by s plus 6. What can we do? Then if you shift this point to this side, these two will be in cascade. This block and s plus 1 by s plus 2 will be in feedback. So you can reduce it. You can reduce 2 steps. Okay. So better we will shift this point to this side. Okay. So in MATLAB, what will you do? We need to define all these blocks first of all. Okay. So let me call this as what I have done is I will define each block, numerator and denominator separately. Okay. Say I will call this as ng1, dg1. So my ng1 is 1, dg1 is 1 space 10. This is my second block. So I call this as ng2. ng2 is 1 and dg2 will be 1 space 1. I call this block as third block. So I call ng3 as 1 space 1. No, because what's the numerator here? It is s square plus 1. That means the coefficient of s is missing. So it should be 0. So what should be my ng3? It should be 1 space 0 space 1. 1 space 0 space 1. Okay. What should be my ng4? dg3. dg3 should be 1 space 4 space 4. Okay. Then this is my fourth block. So I will call this as ng4 will be 1 space 1 and dg4 will be 1 space 6. Okay. Then next thing, this I call it as H1 block. Okay. So what is my NH1? 1 space 1. That is what is written here. What is my DH1? It is 1 space 2. Okay. Then I call this as the H2. Okay. What's the numerator here? It is 2. What about the denominator? It is 1. Okay. So NH2 will be 2. And DH2 will be equal to 1. Now you see here, what's the gain of this path? What's the gain? 0? No. If it was 0, then this channel would not have been there. Okay. Had the gain of this channel, this path being 0, then this path itself would not have been there. Okay. So the gain of this path is 1. Okay. So that means I call this as H3. So what is my gain NH3 here? 1. What is the DH3? That is also 1. That is what is shown here. Okay. So now what we need to do? We need to shift this pick-off point to the right side of this s plus 1 by s plus 6 block. That is what I am doing here. Okay, I am moving the pick off point beyond G4. Okay, now this is not 2 anymore. What happens? That will get changed. Okay, so you are defining a new variable here, new block. Say a one block, what I should call. You will get a new block. Okay, with a numerator n1, denominator d1. Okay, so when you shift this point to the right side, what happens? You will get a new block here. It is not 2 anymore. Okay, so what we need to do? We need to convolute that appropriately. Okay, so that's what I'm doing here. So the new block numerator will be convolution of nx2 and dg4. Okay, and the denominator will be a convolution of dx2 and ng4. I have already explained the block diagram algebra in one of the lectures. Just go through that. Okay, it will be clear. So once you have shifted this point, what happens? These two will be in cascade. So I am using this command, series of ng3 dg3, ng4 dg4. So now this has become one single block. Okay, then what happens? This single block will be in positive feedback with this s plus 1 by s plus 2. That's what I'm doing here. Okay, so this is a positive feedback. So I have given here one additional 1. Okay, don't forget that. Then what? Then this single block and 1 by s plus 1 will be again in series. That is what is shown here. Okay, they will be in series. Then what next? Then this block and this thing, that will be in negative feedback. So that is what is shown here. Okay, are you getting me? Once you shifted this pick off point to the right side, what happens? These two blocks will be in cascade. This single block in cascade and s plus 1 by s plus 2 will be in positive feedback. That single block and 1 by s plus 1 will be again in cascade. That block and this modified loop shifted to the right side will be in negative feedback. That is what I have done here. Okay. Now what happens? That particular block and 1 by s plus 10 will be in cascade. That is what is done here. Then that and this unity gain path will be in feedback. Okay, that is what is done here. So let us run this thing. Okay, I will select this. And I will copy paste it to the command prompt. Okay, so in the last time I forgot to tell you one thing. See, in the command window you can execute everything, but you cannot save. So if you want to save, you need to open a new M script file. Okay, don't forget that. Unless you save it in your M file, you cannot modify or you cannot run it again and again. Okay, once it is executed in the command window, it is done. Nothing more can be done. Okay, so better save all your programs in M files. Okay, so you see what's the transfer function? The transfer function is this thing: s raised to 5 plus 4s raised to 4 plus 6s cube plus 6s square plus 5s plus 2 whole divided by 12s raised to 6 plus 205s raised to 5 plus 106s raised to 4 plus 2517s cube plus what? Plus 3128s square plus 2196x plus 712. This is one way of solving block diagram. Or there is another method. Okay, I will explain that with respect to another problem. Assume that this is the problem that we need to solve. Okay, you are given a new block diagram here, right? 0.5, 4 by s plus 4, 1 by s plus 2, 1 by s plus 3. Then that's a negative feedback with a gain of 2, another negative feedback with a gain of 5, and a unity gain with a feedback of 1. Okay, so how to solve this? So here I will use a different strategy. Okay, I will explain what it is, right? So in this strategy, you just count how many blocks are there first. Okay, so this is a normally in the normal systems, there will not be a block here gain of 1. We will not represent that separately. You will just simply show an arrow. Okay, so an R means you can assume that it is passing through a gain of 1. Okay, so first you need to count the number of blocks here. How many blocks? 1, 2, 3, 4, 5, 6, 7. What is the gain of this path? 1. So it should be 8. Okay, 8. Fine. So I will define this as my block 1. Okay. So in this strategy, you have to define the blocks like Ni's and Di's. That means for block 1, N1 is 1, D1 is 1. For block 2, N2 is 0.5 and D2 is 1. So you do not have a liberty to choose any other variable names. Okay, you need to specify in terms of Ni's and Di's. N1, D1, N2, D2, N3, D3 like that. Okay, so what will be my N3? It is 4. What is D3? 1 space 4. What is N4? 1. And what is D4? 1 space 2. Okay, what is N5? 1. D5 will be 1 space 3. Then N6 will be 2 and D6 will be 1. N7 will be 5. D5, D7 will be 1. Okay, then N8 will be 1 and D8 will be 1. Okay, so you have to define your blocks in this way. Okay, is that clear? In this particular strategy, you need to define the variables as N1, N2, D1, D2, etc. Okay, you cannot use num1, din1 or any other variable name. Okay, you have to specifically define your block numerators and denominators as n's and d's. Okay, then what next? You are telling MATLAB how many total blocks are there. N blocks. There are total 8 blocks. 1, 2, 3, 4, 5, 6, 7, 8. So you have to tell MATLAB how many blocks are there. Okay, so n blocks equal to 8, right? Then the next MATLAB command to be used is block build, BLK build. Okay, we are asking MATLAB to build the block. Okay, so these are all fixed actually. You cannot change that. Okay, in this particular strategy, the naming of the blocks and these commands, they are fixed. You need to follow the same strategy. Okay, what next? Now you have to tell MATLAB how these blocks are connected. Okay, because MATLAB does not know. What did we do up till now? Up till now, we defined each blocks. Okay, and we told MATLAB that there are total 8 number of blocks. Okay, now how are these blocks connected amongst themselves? That we need to define through a connection matrix called Q. Okay, so my Q is called the connection matrix here. Okay, so how to find Q? I will explain. Just give me a moment. Let me complete this. Okay, so Q is an array, right? So how many rows does Q have? Q has that many rows as the number of blocks. How many blocks did we have here? 8 blocks. So our connection matrix has 8 rows. Okay, so the first column will be the block numbers. What did I say? The first column in the Q matrix will be the block numbers. Okay, so block 1, block 2, block 3, block 4, block 5, 6, 7, 8, and so on. Okay, now you need to define how many more columns must be there in the connection matrix Q, in addition to the block numbers. Okay, what did I say? I said after BLK build, we need to define a connection matrix Q. Okay, so in the Q matrix, how many rows will be there? There will be as many rows as the number of blocks. Okay, since we have 8 number of blocks here, there should be 8 rows. That is fixed. Okay, then the first column should be the block numbers 1, 2, 3, etc. up to 8 to indicate that there are 8 blocks. Okay, then we need to define the remaining number of columns. Okay, so how to do that? So you see here, there is one signal channel, one signal path is coming here. Okay, another signal path is coming here. So how many signals do we have here? We have 2 signals, 2 signal paths. Okay, one signal is coming like this, another signal is coming like this. So at this point, we have 2 signal paths. Okay, so now you tell me how many signal paths will be there at this point? 2 are coming from here. This is the third one. This is the fourth one. So here you have total 4 signal paths. Okay, of course, they are algebraically added and summed up. That's a different issue, but there are total 4 signal paths. Okay, so at any point you see the maximum number of signal paths in this block diagram is 4. So that means we must have 4 extra columns in the Q matrix. Okay, so first column will give you the block number. Additionally, there should be 4 number of columns. Okay, I said 4 number of columns. Okay, column 1, column 2, column 3, column 4. Now, what are the entries of the column? Okay, see the first block. Okay, block number 1. Okay, first block. Is there any connection from any other internal? Is there any other internal connection from anywhere? No. So that means the first the entries in the remaining columns of the first row will be 0. 0, 0, 0, 0. Okay, because this signal path R does not have any connection from any other internal blocks or summing points. Okay, there are no internal signals to channel number 1 or block number 1. So all entries in the remaining 4 columns corresponding to row 1 will be 0. Could you digest that? Now coming to block number 2. Okay, block number 2, where are the signals coming from? From block number 1, then 2, 3, 4, 5, 6. Then from block number 1, okay, so here there are total 4 signal channels. Okay, so for block number 2, the inputs are coming from block number 1, block number 6, block number 7, and block number 8. Okay, so from block number 6, the signal is coming at a negative feedback. Block number 7, signal is coming at negative feedback. And again, from block number 8, the signal is at negative polarity. Okay, so what will be the entries? Entries of the remaining columns in the second row should be 1, then -6, -7, -8. Okay, 1, -6, -7, -8. Of course, you can write this in any order. You can write, say, -6, 1, -7, -8. That is not an issue. Only thing is that you should give the correct block numbers with the appropriate polarities. Okay, I will explain once again. When you consider this, we have defined 0.5 as our block 2. Okay, so for this block 2, inputs are coming from block number 1. Fine. This we have defined block number 6. This we have defined block number 7. And this we have defined as block number 8. Okay, so as far as block number 2 is concerned, the inputs coming are from block number 1, plus sign, block number 6, negative polarity, so -6, block number 7, again negative polarity, so -7, and block number 8, again -8. So that is how I got 2, 1, -6, -7, -8. Okay, then block number 3, where are the inputs coming from? From block number 2. Okay, so I can write 2, 0, 0, because there are no other signals from there are no other connections from internal connections. Okay, input to block number 3 is coming totally from block number 2. So 3, 2, 0, 0. Then block number 4, inputs are coming from block number 3. So 4, 3, 0, 0. Then block number 2, 3, 4, 5. Block number 5, inputs are coming solely from block number 4. 5, 4, 0, 0. Now, what about block number 6? Input, where is it coming from? It is coming from the output of block number 3. Is it not? This was block 1, block 2, block 3. So for the 6th block, the input is coming from the output of block number 3. So 6, 3, 0, 0. Then for block number 7, where's the input coming from? 1, 2, 3, 4. So 5, so 7, 4, 0, 0. Block number 8. Okay, block number 8 means this unity gain path. Where is the input coming from? The input is coming from block number 5. Okay, so in this way, you have to complete the connection matrix. Okay, unless you define the connection matrix, MATLAB does not know which block is connected to what other blocks. Okay, so this connection matrix is important. Now, what's the aim? Aim is to find the transfer function between C and R. Okay, between C and R. So you need to tell MATLAB between what is the input and what is the output here. Okay, so my output is coming from the first block, so I am defining IU equal to 1. My output, my input. My output is coming from 1, 2, 3, 4, 5, fifth block output. So I can write my output as IY as 5. Okay, am I clear to you? After defining the connection matrix Q, we need to tell MATLAB which is the input point, which is the output point. Then only you can find the overall transfer function. Okay, so my input is coming from block number 1. So I'm telling my MATLAB input is 1, correspond to the block number 1. Then output, I am fetching it out from block number 5, 1, 2, 3, 4, 5. So I am defining my IY as 5. Then the command is connect. You are asking MATLAB to connect all these things with the help of all the input arguments. Okay, we have defined Q, we have defined IU, we have defined IY. This small ABCD, we have to give it like that. Okay, if you remember, we had defined state space representation where we had x dot equals ax plus bu, y equals cx plus bu. Okay, so here we have to write like this, small ABCD. Okay, we have to write small ABCD, that is mandatorily required. What is a small ABCD? MATLAB will internally generate ABCD matrices for each of these blocks to which we have no access. Okay, but it is required that we have to specify the command connect like this way. We have to first give within the round brackets the small ABCD. Okay, so internally MATLAB will generate ABCD for this block 1, ABCD for this block 0.5, ABCD for this block 4 by s plus 4. Okay, so if you run the command, you will see there will be 8 small a's, 8 small b's, 8 small c's, and 8 small d's corresponding to the 8 blocks. We cannot see that what it is. Okay, but MATLAB requires that we need to specify small ABC. Okay, so with the help of all these input arguments, MATLAB will generate capital ABCD. What is that? That represents the ABCD matrix for the total block diagram, for this overall block diagram. Okay, you will get the final ABCD form, right? Once you have final ABCD form, what do we have to do? We have to convert that into transfer function form. How? With the help of the command SS to TF. That is what is done here. Okay, so you will get the effective numerator and the denominator of the overall transfer function. Then what we have to do? We have to find the transfer function. How? With the help of the command TF. Sys equals TF of num comma d. Okay, I hope that's clear. So let us run this and see what is happening. So you can see here, the state model of the block diagram has 8 inputs and 8 outputs. Okay, so MATLAB will generate 8 small a's, 8 small b's, and so on for all the 8 blocks. Okay, but we cannot access that. So the final transfer function will be 2 divided by s cube plus 13s squared plus 56s plus 80. That will be the overall transfer function of this block diagram. Okay, so this is how to solve, how to use MATLAB for solving a block diagram. So either you can go for series file reduction, or you can make use of this strategy with the help of commands blk build and connect. If you have any doubt, as I said before, you type here help space blk build or help space connect. Everything will be crystal clear. Okay. So I hope this is clear, and we will stop here for the day and meet again with a new lesson. Thank you.